What I want to do in this video is we're going to start going through electron configurations. And electron configurations, it's actually two words there, not one. Electron configurations are not as descriptive as orbital filling diagrams. Instead of putting electrons into orbitals, we're actually putting them into subshells. So electron configurations. So electrons are going to be represented by a superscript number on the subshell. So instead of saying, okay, if I have p orbitals, right? Remember, if we were doing orbital filling diagrams, if I wanted to look at carbon, which we did in the last video, right? We had 6 electrons, and when I got to these p orbitals, I had 1 in each, right? Hund's rule, we put 1 in each before we pair them up. So we're actually putting electrons into orbitals. What we're doing when we're doing electron configurations is we're just going to say that that 2p subshell, I guess it's the p subshell, has 2 electrons in it. So instead of saying that there's 2 separate regions of space with 1 electron in it each, we're just going to say in that p subshell there's 2 electrons. So it's not as descriptive. I do want us to be able to do both. So not as descriptive as orbital filling diagrams. Because electrons are shown in subshells, not necessarily individual orbitals. And the reason I'm saying not necessarily instead of just not is that if we're looking at an s subshell, there is only one s orbital per subshell. So in the case of s's, putting them in a subshell and putting them in an orbital are actually going to be similar, right? There's only one s orbital per subshell. But with p's and d's and f's, not so much. So not as descriptive as orbital filling diagrams because electrons are shown in subshells, not necessarily individual orbitals. So we're still going to give the number of the shell, the letter of the subshell, but then I'm going to put a superscript number on that subshell to indicate the number of electrons. So this was carbon here. If I wanted to write my electron configuration for carbon, and our energy is just going to increase left to right, so I'm just going to write it on one letter. I have my 1s orbital, and I have 2 electrons in it, so I'm going to put a superscript 2 on that s. Next, I have 2s, it has 2 electrons in it. And then I have my 2p subshell, right? And it has 2 electrons total. So again, it's not as descriptive because our electron orbital diagram, right, is showing 2 separate regions of space for the p's with 1 electron in each. Here I'm just saying the p has 2. We often are going to use electron configurations because it's just quicker. So if I want to show something real quick, I'll use electron configurations. But again, orbital diagrams are giving us a better representation of where those electrons are. And then as I mentioned in the last video, just be careful on an exam that if I ask for electron configuration, you don't give me orbital diagrams and vice versa. So this was our orbital filling diagram. This is our electron configuration. I'm going to scroll back up to the bromine one we did in the last video, which is just right here. And if we were to write the electron configuration for this one, so I'm just going to start at the bottom. So I have 1s, I have 2 electrons in it. Then I have 2s, it has 2 electrons. Next is 2p, here I have 2, 4, 6. 3s, which has 2 electrons in it. 3p, there's 6 of them there again. Now up here, So 4s with 2 electrons. 3d is next. And if we count, I have 2, 4, 6, 8, 10 electrons. Next is 4p, and it has 2, 4, 5 electrons. So this would be my electron configuration for bromine. So again, it's similar. Energy is increasing from left to right. I'm showing my shell number, my subshell letter, and then the superscript is telling me the number of electrons in that subshell. So I said I would give you a shortcut using the periodic table to remember the order of our orbitals. So again, I'm scrolling back up through all that stuff we did in the last video, but this table, right, our quantum numbers is really kind of our order, right? The reason there is 2 subshells in my second shell is because of this, right? This equation. The reason I have 3 different p orbitals is because of this, right? My quantum numbers. The reason I can have 6 electrons in that p subshell is because of the Pauli exclusion principle, right? And there's only 2 values for m sub s, so 2 electrons maximum per orbital. Again, I am going to show you a shortcut, but again, the periodic table is only going to be my shortcut. It is never going to be my answer for any of those questions. So do be careful on that. So I'm just going to go out to our periodic table, and then I'm going to start marking it up. So the first thing I'm going to do is I'm going to relocate helium. So I'm going to take helium from over here, and I'm going to move it over here. So helium has been relocated. And then I'm going to take my first 2, let's actually use highlighter. I'm going to take my first 2 groups, of which helium is now part of, and that is going to be considered my S block. And then I'm going to put an N in front of it. N is going to correspond to whatever my period number is. So hydrogen, its value for N is going to be 1. It's in the S block. After I'm done, I'll do some examples after I'm done dividing all of this out. So I'm going to go over here, and we're going to grab the rest of our main groups, ignoring helium because we did relocate him just for these purposes. Doesn't permanently belong over there. And these are going to be my P block, and I am going to put an N in front of it again. These ones in the middle here, my transition metals. These are going to be my D block. And then in front of it, I need to do N-1. Remember that the energy of my D subshell is actually higher in energy than the S subshell of the next shell. So if I'm in the 4th shell, my 3 Ds are actually going to be the next ones that come in energy. That probably didn't make a lot of sense, and I'm sorry. I really will do examples, and hopefully it will make sense then. One more, and that's going to be these. These are going to be my F block. And we'll write underneath it. I didn't do any examples with Fs in the last video, but we gave those a double asterisk when we were talking about our energy when we did that table. We said that they're higher in energy than the S orbital of 2 shells later. So I'm actually going to subtract 2 from this, and then these are going to be my Fs. So if I wanted, and you can do this for electron configuration or orbital filling diagram, I'm going to do electron configurations. You essentially find the atom that you're trying to do the electron configuration of. So let's actually just start with carbon because we've done that one already. So I'm going to find carbon on my periodic table, and it's right here. Just highlighted it in yellow. And then we're literally going to count every square till we get to carbon, kind of in order. So if I look to start, I have 1, and then this is going to be S, and then there's 2 squares. So I'm going to write 1s2. Since I moved helium, there's no, if we look right here, there's nothing. So there's no 1p's, right? I'm still in shell 1, right? Because my value for, or my number for my group is my value for n. There's nothing there. And again, be careful on a test. If I ask you why there's no p orbital or p subshells in the first shell, your answer is not that there isn't space in the periodic table, right? It's because 1 minus 1 doesn't equal, or 1 minus 1 doesn't equal 1, right? It's that quantum number explanation that we went through in our first video. So do be careful. After that, I'm now down here, so I have 2. I'm still in the S block, and there's 2 squares. So 1, 2, so 2s2. I'm now in the 2p's, right? I'm just going across. So this one we counted, this one we counted. So that was my 2s2. I'm now over here in my p block. I'm still in the second period, so it's still 2. And then I'm going to stop when I get to chlorine. So, or sorry, carbon. I'm in the p block. So 1, 2. So 2p2 would be its electron configuration. You literally are just counting every square till you get to the atom that you're looking for. Let's do something that has D's. Let's do cobalt. So cobalt's right here. And again, I'm just going to start with 1 and I'm going to count all of them. So I'm in the first period, there's 2 squares. So 1s2. Now I'm in my second period. I'm in my S. There's 2 squares, so 2s2. I'm still in period 2, but now I'm in my P's. There's 1, 2, 3, 4, 5, 6, so P6. I'm now in my third. I'm back to S. There's 2 squares, so oops, 3, not 2. 3s2. I'm still in period 3. I'm in my P's now. 1, 2, 3, 4, 5, 6. I'm now 4. I'm still S, or I'm back in S, I should say. There's 2 squares, so 4s2. And then notice I'm now going to be in my D's. D's going to come next, but I have to subtract 1 from whatever my group number is, or my period number is. So instead of writing down 4D, I'm going to write down 3D, right? I need to subtract 1 from that 4 that has so many circles around it you can't see it. So it is 4, but I have to subtract 1 from it, so 3D. And then I'm going to stop when I get to cobalt. 1, 2, 3, 4, 5, 6, 7. So 3D7 would be its electron configuration. So again, we're just counting everything till we get to it. If we wanted to look at bromine, right? Bromine is right here. I would do 3D. It's what we have for cobalt so far, but I would keep going. So that would be 10, 3D10. And now I'm back, right? For my P's, it's just N. So it's 4P, 1, 2, 3, 4, 5. And if you go and compare that to what we did without the periodic table, the answer will be the same. I'm going to get rid of that stuff so we can do another. I do want to do one with F's next, so we can go through the whole thing. So giving myself some more room. We're going to have to write kind of tiny on this one. Okay. So let's do lead. So lead is right here. So remember, these 2 groups down here, my inner transition metals, they're part of periods 6 and 7. So as I'm going across the periodic table, after barium, right, after this one right here, I'm going to have to go down and do that row. So don't forget where they belong. I want to get those lines back. Okay. So I'm not going to cross everything off. We'll just kind of get going on it. So I'm doing, what did I say, lead? So writing at the top. So starting at the beginning, we'll get going, but I have 1, I have S, and there's 2 squares. So 1S2. There's no anything else for 1, so now I'm at 2. I'm still in S, there's 2 of them. Right, going across, oop. Right, I'm now here. So 2P, there's 6 of them. So that finishes off my second period. I'm now in my third period. S's first, there's 2 of them. There's no D's in period 3 currently, right? I mean, there are D subshells, right, in shell 3. It's just that the energy doesn't come until after the 4S. So be careful. The periodic table, again, is our shortcut, but we don't want to use that as our answer. So back to where I'm at. I'm right here. So I just did 3S2. I'm now going to do 3P6. I'm now on period 4, 4S2. After 4S2 comes D's. I need to subtract 1, so 3D10. And now I'm back into my P block, which I don't subtract 1 from. This was just NP. And there's going to be 6 of those. 1, 2, 3, 4, 5, 6. I'm now on period 5. 5S2. I'm now into the D's. I have to subtract 1. So 4D10. I am back to my P's where it's still 5. So 5P6. So that finishes out that whole row. I'm now at 6. I'm in the S's, there's 2 of them. And then this is where we have to go down and do our F's. And then for the F's, I have to subtract 2 from it. So instead of doing 6F, I'm going to do 4F. Remember, my F orbitals are higher in energy than the S orbital of the next 2 shells. So 2 shells up from 4 is 6. That 6 is going to be lower in energy than that 4F. And then if you didn't count, you would know how many there are, right? There's 7 orientations, 2 electrons max. So if we were to count these, there is going to be 14. And again, we don't put 14 electrons in the F subshell because there's 14 spaces on the table. That's not why, right? That's reverse logic. Right? The reason we have 14 electrons is that there's 7 different orientations of that shape, right? So I have 7 different orbitals, and we can put 2 electrons maximum per orbital. After those, I'm now back up here, right? If we're just following our numbers, after 71, I'm back up. So I now have, right, we're in period 6. I'm going to subtract 1 to get my D's. So I have 5D10. I'm now over here in my P's. I'm back to 6 because we don't subtract 1 for my P's. And then I just count to get to lead. So 1, 2, P2. We can squish it on there. So that would be my electron configuration for lead. I do want to show you some shorthand notation for writing these. And I don't always let you use the shorthand notation. I do want to know that you can write the entire electron configuration first, and then I'm okay with doing the shortcut. But I do want to show you that shortcut. And I'm going to do the electron configuration for something smaller real quick. Let's just do phosphorus, and then we'll come and we'll do it for both of these. So phosphorus is right here on the periodic table. So I'm just going to go through it real quick. So 1s2, 2s2, 2p6, 3s2, and then I'm in the 3p subshell, 1, 2, 3 to get to phosphorus. So this would be my electron configuration. So what we're doing with the noble gas shortcut, and I will write these directions once we go back to the regular page. But you're finding the noble gas that's one period above the element in question. So we're drawing the electron configuration for phosphorus. That's in period 3. I'm going to go up one period to period 2, and that's going to be neon. Remember, noble gases were group 18 or 8A. So what we're doing then is we're going to write the symbol for that noble gas in brackets, and then we're just going to write everything that comes after it. So essentially, if I was to write the electron configuration for neon, it's going to be this, right? 1s2, 2s2, and then 2p6. That's my electron configuration for neon. So what we can do, instead of writing all of that, I can just write neon in brackets and then write everything that comes after that, which is the 3s2 and then the 3p3. So I know everything's getting squished in here, but this would be the electron configuration for phosphorus using my noble gas shorthand notation. Now again, I don't want you to always use it because I want to know that you can write this whole thing. And if you always use this shorthand notation, I don't know that you can do that. For example, if you were to do the shorthand notation for lead, right? Finding lead on the periodic table, it's down here. I'm going to go up and I'm going to write xenon in parentheses, because that's the noble gas that's above it. Sorry, I keep bumping my arm on the keypad there. Sorry, I can't seem to stop doing it. I guess I just need to not write so high. There's no place else to put it. Let's squish it in here, xenon. So xenon's right here, right? And then I'm going to write everything after it. So the 6s, 6s2, and then I'm going to go and do those 4 F's. Remember, you have to subtract 4 or subtract 2 from whatever your period number is. There's 14 of them. And then my 5d10, and then 6p2. So that would be my shorthand notation. Basically everything up to that 6s, if I was to write the electron configuration for xenon, that's going to be it. So then we can just write everything that comes after it. But again, I want to know that you know that order. And if you always just use the shorthand to start with, I'm not going to know that you know it. So eventually I'm going to be fine with it all the time. But initially, please don't unless I explicitly say. So like on a problem set or a quiz, if it doesn't say that you can use the shorthand notation, please don't. By the next chapter, once we get to chapter 4, I'm fine with you using it. But in chapter 3, please don't use it unless I say that it's okay. And I will say, I'm not going to always have you write the entire thing out. So going back, our noble gas shorthand notation. So essentially what we're doing is you're writing the noble gas, or the atomic symbol, we should say, for the noble gas that is one period above the element in question, in brackets. So brackets. And then write the electron configuration for everything after it. And by everything, I don't mean everything. I mean up until the element that you're trying to write the configuration for. So everything that you need to after it, if that makes any sense. Hopefully it does. So let's clear some of this mess off the periodic table and just do one more here. I'm running out of room. It's probably getting hard to see this. And then see if I can not erase the stuff I don't want to erase. Okay, that stuff can stay. So let's do tin. Tin is right here. So please do this one on your own. Write the whole entire configuration and then also do the noble gas configuration. And then hit pause, do that. And then when you're ready, hit play again and you can check your work. But I do want you to try one on your own. Okay, hopefully you guys did that. And I get 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Did you guys remember to subtract 1 from your period number when you got to your d's? And then 4p6, 5s2, 4d10, and then 5p2, because that's where tin is. So that would be my configuration. If I'm going to do my noble gas shortcut, tin is in period 5. I'm going to go up to period 4. I'm going to write the atomic symbol for krypton in brackets. It does need to be in brackets. And then everything that comes after that, so the 5s2, jumping the gun here, 4d10, and then 5p2. So that would be using the noble gas shortcut. There are a couple electron configurations that turn out to be different than what we would predict using our rules. So these are going to be anomalous. Anomalous just meaning they're different than what we would expect. So anomalous electron configurations. So the electron configuration for some atoms or elements, you could use the same word here, or either word here, sorry. The electron configuration for some atoms is different than what would be predicted using the off-bell principle. Remember, that was the one that said that we want to put electrons in lower energy orbitals before higher energy orbitals. And I don't necessarily expect you to know when an electron configuration is anomalous, but if I tell you that a particular element has one, I do want you to be able to draw it. So an example of one is going to be copper, and we'll do that one in a minute, but the kind of the reasoning for it is that if you have filled or half-filled subshells, they're more stable than subshells that are neither filled nor half-filled. So filled or half-filled subshells are more stable than subshells that are neither filled nor half-filled. So having, say, in a p subshell, right, it can hold 6 electrons total. So having 6 electrons or 3 electrons, right, half-filled, either one of those is more stable than having 1 or 2 or 4 or 5. So having filled and half-filled subshells are actually more stable. So copper, if I was to look at copper, and I draw its electron configuration, I'm just going to do this using the periodic table. So if you have it in front of you and want to pause and try to draw it yourself, that would be perfect. if I was to write the shorthand notation for this, all of that would have the electron configuration of argon. So we could write argon 4s2 3d9. So it's anomalous configuration. If I look at this right now, my S subshell is filled, right? S's can hold 2. My D subshell is neither filled nor half filled. But if I was to take one electron from that S subshell and bump it up to that D subshell, I now have S being half filled and I have D being filled. So I'm actually increasing its stability, decreasing its energy by doing that. So this is my predicted, right? Using the rules that we've gone through, this is my predicted configuration. This is my actual configuration, because even though I'm moving an electron up to a higher energy orbital, because I'm achieving this, it's actually going to be more stable or lower in energy. So I'm going to take one of those S electrons, right? So instead of having 4s2, I have 4s1, and I'm going to move it up, and I now have 3d10. So this is filled, and this is half filled. So before I fixed it, right, I had one subshell that had relative stability and I had one that didn't. Now I have two that both have relative stability. So that's going to be more stable. And again, I don't expect you to just know that copper does, but if I say copper has an anomalous electron configuration rather than predicted an actual one, I do expect you to be able to recognize that if I was to take one of these electrons and move it here, I'm getting this part. So do be able to do that. Another example of something that does would be chromium. So give this one a shot yourself. So draw the predicted, and then it does have an anomalous one. So see what you can do to make it better. And it's only going to do this, it's only going to make this jump if the orbitals are close to each other. Like don't take something from like a 2s and bump it up to like a 4s. Like that's not cool. It's just going to be one move. Otherwise you're increasing it, and like the energy of that bump is so great that it doesn't, right? This isn't great enough to overcome that energy. So just a small move. Okay, please do this one on your own. And then when you're done, hit play again. Okay, I am gonna draw my noble gas shortcut for this one. So I have argon, and then 4s2, and then 3d 1 2 3 4. So this is my predicted. If you drew the entire configuration out, the part that you're missing is this part. So you can check your work by just seeing if you have that, or the part that I'm missing is that. So if you have that, you drew it correctly. So if I look, d orbitals, remember, can hold 10, so 5 is actually going to be half filled. So what I'm going to do is I'm going to take one of my 4s electrons, so I now just have one there, and I'm going to move it up to my d. So this is going to be my actual, or my anomalous configuration. So these are both half filled now. Before I had a filled and something that was neither, now I have two half filled subshells. So that's actually going to make it more stable.